Also is an associate professor of theoretical physics at Free University of Amsterdam, and also he's a member of theory group of NICEF, the National Particle Physics Institute of Netherlands. He obtained his PhD in Barcelona following postdoctoral position in Paris, Milan, and CERN. He moved to the University of Oxford for his first faculty position before ending up in Amsterdam. His research focuses on understanding the action of the proton with machine learning techniques and searches for new physics using effective field theories, and also he is interested in precision calculation of neutrino scattering. So without further delay, I'll zoom over to Professor Hyun. Yeah.
Thank you. Can you hear me?
Yes, we can hear you and we can see the. We can get started.
So thank you very much for the invitation. As Isabel said before, it's a pity not to be there in person, so hopefully in the future we can remedy this. So in this talk, I want to tell you a little bit about proton structure, in particular about how we evaluate the momentum distributions of the protons in terms of quarks and gluons, and why this is important for Higgs physics. And of course, a proton structure has played an important contribution to the discovery and the characterization of the Higgs boson, because at the LHC being a proton collider, unless we understand the proton, we cannot really do precision measurements there. So why do we study proton structure at all? You could think that the proton is a perfectly well understood particle, right? After all, we've known the proton for a long time, almost more than a century since the original Rutherford experiments that discovered that the atom is composed by electrons and then by a very small nuclei composed by protons and neutrons. So then we should know everything about the proton. Actually, this is not, and the reason is that what is the proton itself is not a well-defined question. The proton is a quantum mechanical object, and then what the proton is depends on the resolution scale to which you look at it. So in other words, it depends on the energy of the probe that you use to examine the proton. So if you look the proton from afar, it just looks like a point particle. And here afar means distances, say, much larger than a femtometer, and energy is much less than 1 giga-electron volt. However, once you start to dig a bit deeper, for example, if you use probes with an energy of a few GeV, you discover that the proton is not elementary. Actually, it's a composite object, which is composed by two valence quarks, 2 valence up quarks and 1 valence down quark. If you keep increasing the energy of your proof, so if you reduce the resolution scale, you start to find a richer structure. You find the gluons, you find C quarks. And then if you go to higher and higher energies, you discuss a plethora of phenomena. You discuss the proton can contain heavy quarks, charm, proton, and even top, photons, leptons. And if you are at high enough energies, you might even find Higgs bosons. And the question is simply because at asymptotically large energies, all standard model particles become massless, and therefore, just by big lab evolution mixing, you will also have a Higgs contribution in your PDF evolution equations. So the proton is also really a unique probe for us to understand the strong interactions. So the fact that we can write down the Lagrangian of QCD doesn't mean that we actually understand what the strong interactions and all the phenomena contain there. And in the last few years, we've been unraveling more and more interesting phenomena of the proton. For example, we discovered a few years ago that the gluons provide a significant contribution to the proton spin. The fact that the proton is a spin 1/2 particle doesn't mean that we understand where this 1/2 comes from. It's a fundamental question. We have found that the proton under certain circumstances can be found as a gluon-dominated state. So basically, only the gluons dominate the big lab evolution. This was called the BFKL resonation. We have understand the proton, it has a very peculiar antisymmetry structure. So if you look at the antimatter asymmetry of the proton, this is something that is, say, quite different from the expectations based on naive models. And recently, and I will discuss this in my talk, we have evidence that the proton contains not only up, down, and strange quarks, but it also contains charm quarks. This is the so-called intrinsic charm scenario. So in this respect, understanding about the proton structure is key to address fundamental questions about quantum chromodynamics, such as the origin of mass of spin, the heavy quark content, or 3D imaging, or nuclear modifications. But also, even if you don't care much about QCD, or you always say to discover new physics, you need to learn about the proton, because for searches for new elementary particles beyond DSM, as the ones that Isabel has discussed in her talk, if you want to learn about what is the origin of cosmic neutrinos, or about what is the quark-gluon plasma heavy-ion collisions, you need to know about the proton, because all these three types of experiments, they depend sensitively on the behavior of the quarks and gluons inside the proton. So then we would like to understand about the proton also because to provide precise predictions for experiments in particle, nuclear, and astroparticle physics, of course at the LHC, but also at electron-proton colliders, the existing ones, ERA, and the future ones, such as the Electron-Ion Collider. For neutrino physics, experiments such as IceCube, KM3Net, and eventually something called the Forward Physics Facility, which I will explain at the end of my talk. But also for heavy-ion collisions such as proton-lead collision at the LHC, proton-lead, or at also the Electron-Ion Collider. So there is always this double motivation to understand the proton. On the one hand, to learn more about QCD. On the other, to provide robust predictions we can use for many experiments in a wide range of applications. So the main topic of the talk is Parton distributions, which are the objects that describe the motion of the proton constituents in high energy collisions. So the idea is that the proton is like some kind of recipient and contains a bunch of constituents, and the energy, the spin, and any other property of the proton is shared among its constituents. And these are the quarks and the gluons. And we call Parton distribution functions, or PDF for short. These are the objects that determine the amount of momentum that a given proton constituent carries inside the proton. We cannot compute these quantities from first principles because they are determined by non-perturbative QCD dynamics. So we have to extract them from the data using the so-called global QCD analysis. Recently, there has also been lots of exciting progress in lattice QCD calculations, indicating that in the near future, lattice QCD can provide a key contribution to these global feeds of Parton distribution. For the time being, we have to extract them in a phenomenological manner. So how do we extract PDF? The idea is simple. You take two protons, you collide them, and then you predict the outcome. For example, what is the outcome? What are the number of Higgs bosons that the LHC will produce, say, in 1 year? If you look in your QCD textbook, you will see that the number of Higgs bosons has two components. First, it depends on the partonic matrix element, that is gluon-gluon scattering going to a Higgs. But also, you need to know how many gluons the proton contains and what is their momentum distribution. Because only gluons with the right amount of momentum will be able to produce a Higgs boson. So while this partonic matrix element can be computed in perturbation theory, order by order, the initial state, so the gluon luminosity, cannot, and therefore needs to be extracted from data. And this structure, actually, it holds to all orders in perturbation theory, thanks to the powerful QCD factorization theorems that guarantee that even when you include radiative corrections, you can still separate the UV dynamics from the infrared dynamics in the PDFs. So what is this object, the PDF, let's say for the gluon? What is gluon of X and Q? So G indicates the probability, at least at leading order, of finding a gluon inside the proton, which carries a fraction X of the momentum. For example, gluon with X of 0.1 means a gluon which carries 10% of the proton's total momentum. And Q is the resolution scale. So it's the energy of the hard scattering collision, which, as we know from quantum mechanics, is the inverse of the resolution length. The higher the Q, so the higher the energy of the partonic collision, the smaller, so the better the spatial resolution at which you are proving the proton. So the dependence on X, on the momentum fraction of this PDF, is determined by non-perturbative QCD dynamics, and therefore we have to extract from the data. So basically, we have to produce a model for the PDFs at some initial scale Q0, and this model will depend on some parameters, say A sub G, A sub G1, A sub G2, which I will constrain from the data. Now, fortunately, this is not purely phenomenology. I can also use theory to constrain the shape of the PDFs. In particular, these PDFs have to obey fundamental symmetry, such as, for example, quark number conservation, which tells me that up minus up bar integrated over 0 and 1 must be 2, just because the proton contains 2 up quarks. And energy conservation, which means that if you add up the energies carried out by all the quarks and the gluons in the proton, you just get the proton energy. This is called the momentum sample. So these two conservation principles help us to constrain our PDFs. Furthermore, the dependence on Q is actually perturbative. So you can express the dependence of the PDF with the scale Q in terms of this integral differential equation, where the derivative of PDF with respect to the log of the resolution scale is the convolution of the same PDF times some kernel, which depends only on the splitting function alpha s. So you can compute order by order in perturbation theory, and we have results up to n to the cube leading order, so that's next to next to next to leading order, and even some results one order higher. These are the famous Dirichlet-Parton evolution equations, which are at the core of our ability to predict anything at the LHC. So without this information from QCD, at the LHC you cannot really do any predictions. So this is a snapshot of the proton structure, how the PDFs look like. Left is a 10 GeV square, and then right is 10 to the 4 GeV square. So this would be the scale at which the Higgs boson would be produced. So if we first look at lower scales, we see that at large X, the proton is dominated by the valence quark. This is up, valence is up minus up bar. And why up valence is about twice as large as down valence? Well, because the proton contains two up quarks, while only one down valence quark. And then you have the C contributions. So you have up bar, D bar, S bar, charm, and also the gluon divided by 10. So as you go from large X, so large momentum fractions, to small x, small momentum fractions, the gluon becomes more dominated by C quarks and for the gluon. And if you look at a typical LHC scale, at which you produce a Higgs boson, then the valence PDFs are more or less the same, but there is a very steep rise of the gluons and the C quarks. Particularly, you see that, for example, strangeness or even charm PDF are not too different from the up bar and down bar PDF. Now, the gluon, which becomes very large. So this shows you that in high energy collisions, such as the ones that are accessible at the LHC, you have a very strong contribution from the C quarks and the gluons. While in previous colliders, say at the Tevatron, the contribution was mostly driven by the valence quarks PDFs. Of course, if you go to higher colliders, the situation becomes even more extreme. So at the FCC, for example, you will typically be able to access collisions of 10 to the minus 6 or so. So then the FCC is to some extent an ultra small x QCD machine. So how do we extract these PDFs in practice? As I said, thanks to QCD, we can factorize, say, a scattering cross-section. In this case, take a charged muon and launch it with respect to a proton target, and then measure the recoil of this outgoing muon. This is called the deep inelastic scattering process. Since this quantity here on the left can be measured, this is simply the number of muons that you measure with a single kinematics. And this quantity here, this is the partonic matrix element for the scattering of a virtual photon with an up quark. You can compute in Feynman diagrams. This is a very simple calculation at leading order in QED. Then the only unknown is the PDF of the up quark. So essentially, predicting this quantity here requires computing this matrix element and then doing a convolution with the up quark. So then you see, I measure this, I compute, so the only unknown is the up quark. Basically, this is the process. You have a lepton. This lepton emits a charge, a virtual photon, and this virtual photon interacts with the content of the proton or with nuclei to then provide information about the partonic structure of the proton. So now I go to the LHC and I said, that's very good because I've measured the up quark PDF. And now if I want to predict, for example, W production, then that's easy because I have here the up quark and the down bar quark, which I've measured. The matrix element for UD bar going to W, I have computed beforehand using, again, Feynman diagrams, and then you get the full result. So the idea is to use the PDFs, measure them from some process, and then use them to predict proton-proton collisions. Of course, these are a big simplification. In practice, you cannot really measure PDF. You have to deconvolute them from the data, basically by solving the inverse problem. But this is the gist of the situation. This is how we extract the PDF. We take, say, data A, B, C. We interpret them in the context of QCD. We extract the PDFs, and then we use them to predict process D, E, and F. Especially this is possible because PDFs are universal, which means that they are identical in every process, irrespective of the prof. So they are the same in neutrino DIS, charged lepton DIS, or proton-proton collisions. So this is what we define by the global QCD analysis paradigm. First of all, you have to parameterize the PDFs at the boundary, say around 1 GeV, between perturbative and non-perturbative QCD. So if Q is below 1 GeV, QCD stops being perturbative, and then you cannot say much about them. So typically the PDF, this is a good scale to parameterize them. So you write your model for the PDF, which is, I remind you, the dependence with momentum fraction x, as some function that depends on a bunch of model parameters. And depending on how ambitious you are, you have more or less parameters. Then you take these PDFs, you evolve them using DigLab, you combine them with the partonic matrix elements, and then you end up with a prediction for LHC cross sections, which depend on these parameters A. Okay, so you will have a series of predictions which depend on the parameters of your PDF model. And then you take your predictions, you compare them with the data, and then you solve a maximum likelihood optimization problem, and you obtain the best fit values and the errors on the parameters. So typically, you construct some kind of chi-square. This chi-square depends on the model parameters, A sub k, and then you minimize this chi-square, and you find the A sub k that get you to the best description of the data. And then one has to account for the various uncertainties, which is a topic by itself. Key point is that once you have this, the PDFs, so with this model for the PDF with the tuned parameters to the data, is ready for applications for any process that involves proton or nuclear targets and projectiles, because PDFs are universal. Once I determine them, I can use them to any other process that involves high energy scattering with protons or with nuclei. So what is the situation of PDFs now that the run 3 is starting? So there are several groups that provide regular updates of their PDFs. So the group that I'm involved, NMPDF, released in September last year the latest version, NMPDF 4.0. And this was a significant update of our PDF analysis, especially because we released not only the grids itself, but also the full-fledged fitting code as an open source Python framework. So anyone in principle can take our fitting code and produce their own set of PDF analysis. And as I will explain, we use some interesting machine learning techniques which aim to reduce any human bias or model dependence. Other groups such as MSHT, CT18, and AVMP also release regularly updates of the analysis. For example, MSHT20 released in December 2020 their grids. And there are also interesting discussions about the settings chosen from each group. But I don't want to make this talk too technical, so I will keep it more about the concepts. You can ask me if you have interest. And in addition to the individual sets, there are also combinations. So we've learned from previous experience that sometimes in experimental analysis, it makes sense to pre-combine the PDFs beforehand and then use this combination in the analysis of the data, because this facilitates, for example, the evaluation of the PDF errors if there is a single PDF set. So in March this year, we released the PDF for LHC21 combination, which is the official combination which we recommend to be used for many run 3 PDF analysis. And it combines CT18, MSHT20, and NMPDF 3.1. And there are also other analyses from Jam Collaboration, HERA PDF, Atlas PDF. So there's a lot of activity in Proton PDF right now.
One?
Yes.
I have one question. What exactly are you parameterizing in terms of these functional forms, Chebyshev polynomial, Bernstein polynomial?
Yes.
So
yeah. You have to parameterize. For example, you say that the X gluon PDF is some function of X, which you don't know. And you can parameterize it with neural networks, Chebyshev polynomials, or with whatever model that you would like.
Okay.
So this is the typical data set that we use in our feeds from NMPDF 4.0. It contains around 5,000 independent cross-sections from almost 100 different data sets and lots of different processes. And this is important because to extract all the PDF combinations, you need both a broad data set in terms of kinematic coverage in X momentum fraction and Q resolution scale, but also in terms of sensitivity to the PDF. So Drell-Yan, for example, constrains some PDF combination, Jets constrain another, and so on. So the more data that we can add, the better. And actually, in modern PDF feeds, at this point, almost 1/3 of the data set is composed by LHC measurements. which is quite interesting because 10 years ago, there was essentially no PDF feed with LHC data. And now they are on their way to becoming the majority of the data using PDF feeds, which is also a sign of the success of the LHC to provide information on hadronic structure and on the strong interaction. One can discuss a little bit how each data set, how each PDF feed contains various data sets. Again, this is a very busy table, but just to give you a flavor that, we take a lot of effort trying to investigate which of the LHC measurements can be used for PDF feeds. We have to produce the corresponding theory calculation using the highest possible accuracy. And then we have to massage these results to implement them into a PDF feeding framework because, say, the output of a Monte Carlo program is not sufficient. So one needs to prepare a very specific fast interpolation framework to use them in the PDF feed. And then various groups make different choices of their inputs. And you can see that, for example, NMPDF 4.0 is the PDF set that includes more data from the LHC and also from other experiments.
So why don't you use 5-star measurements?
Sorry, why don't we use why?
5-star. You use ZPT, etc. WZPT. Yes. But why not 5-star? 5-star.
Yeah, 5-star. Yes, that's a good question. I think first we cannot include at the same time ZPT and 5-star because that would be double counting. But in general, the problem is that the data with 5-star is extremely precise. Yeah. And it's actually, if you try to compare to produce a chi-square with NL or QCD, you get a very poor result. You have to include resummation corrections. You have to include also some, Parton shower effects and so on. So it's an observable which is not really suitable for PDF feeds in the sense that it provides information that requires a lot of theoretical improvements before it can be added to the PDF feed. The ZPT is much more transparent because this is simply you can write it down as by quark glue and scattering.
Okay, thank you.
Okay, so again, some comparisons. I don't want to bore you with details, but the point is that in general there is good agreement with other groups, for example, CT18 and MSHT20. But there are some interesting exceptions. For example, our gluon can be quite different at large X, or also we can have quark separation differences. And in some cases, this can be understood based on the choices of data set, other because of methodology, and we are actively discussing with other groups also to try to understand what's going on. And it's good, of course, that different groups analyze the same problem independently. In terms of uncertainties, you can find a pattern that CT18 has the largest uncertainties, followed by MSHT20, and then NMPDF 4.0 is the most precise. And one possible explanation for this is that the data is the same pattern. So the data that we use is bigger, the data used for MSHT20, and bigger from the data from CT18. Now, what makes this PDF analysis, what has been going on in the PDF fitting community in the last years? First of all, adding many more new processes, for example, adding digest production, adding collider Drell-Yan, which is key for strangeness, adding the sequenced Drell-Yan measurements from the proton antimatter asymmetry, adding differential top quark production. These are many processes that didn't exist until a few years ago. And also, not only now they're available, they have very good precision, and they provide strong, if not the dominant constraints on many of the PDF combinations. For example, the collider measurements of Drell-Yan production, so W and Z production, provide the leading constraints on the proton strangeness together with the neutrino data. So the LHC is not just providing some footnote on the PDF feeds, it's literally dominating the information on the PDFs that we extract from the data. We are also working very hard in improving the theory calculations because, of course, you can have excellent data, but if you have a very poor theory calculation, you cannot really extract the PDFs. And this includes computing QCD corrections up to higher order in perturbation theory. So NNLO is now a standard, and N-cube leading order is becoming available for many processes. In this case, this is for Drell-Yan, neutral current Drell-Yan production. A comment, I will be back to this, that so far we miss PDFs at n to the cube leading order. So we have calculations in QCD at n to the cube leading order, but not PDFs. And this mismatch will affect, in general, the accuracy of the calculation. We also include electroweak corrections. We include theory constraints such as PDF positivity and PDF integrability. And there are also studies that show that you can also include lattice QCD constraints to provide information on the PDFs. Basically, you include them as theory data. For unpolarized PDFs, lattice right now cannot make a big impact. But for example, for polarized PDFs or for nuclear PDFs, the information from lattice is likely to be more valuable. And this is something that we are discussing actively with our lattice QCD colleagues, trying to see how can we improve these determinations. Now, going back to the question, so how do we parameterize our PDF? So which model do we choose? It depends on the group. So, for example, MSST uses Chebyshev polynomials. In NMPDF, we choose artificial neural networks. So essentially, we choose an architecture such as this one. The inputs are X and log X. Then we have two hidden layers. Then we have an output layer, and each of the nodes of the output layer corresponds to a specific PDF combination. For example, the gluon, total quark singlet, which is the sum of quarks and antiquarks, and so on. And then we can also play various games to demonstrate that this parameterization is flexible enough and that it can actually provide a bias-free prediction of the data. In particular, we can parameterize the output of a neural network into different bases. So we can use the physical basis, up bar, d bar, or we can use the so-called evolution basis, which is the DGLAB eigenvalue basis, gluon, sigma, valence, and so on. Of course, it's just a basis transformation. And we know from our first year linear algebra course that results should be basis independent. But for the first time, we have shown in this work, actually, the global PDF fit is exactly the same if you choose one basis or another. How do we train these neural networks? So we use stochastic gradient descent as available in the TensorFlow package. And then we have some what's called a automated model hyperparameter optimization, which means that, for example, the architecture of the neural networks, the number of neurons, number of layers, the minimizer and the learning rates are not chosen by trial and error. We have a procedure that automatically sets up what are the best values of these hyperparameters. So in our approach, we constrain not only the model parameters, but also the hyperparameters directly from the data. And then we have a battery of tests to make sure that our results make sense statistically. For example, something called closure test, which is that you assume some underlying truth from our theory. So you say, I'm God, and now the PDFs have exactly this form. You that based on this truth, and then you repeat the analysis. And you verify that indeed you can reproduce what you're putting in. And I can provide more details about this if people are interested. Let me show you how our method works in practice. So what we do is we estimate errors using the Monte Carlo replica method, which in a nutshell, it means that I'm going to generate copies of the experimental data using Monte Carlo fluctuations, and then I'm going to train a neural net model in each of these replicas. And afterwards, the envelope of the resulting models is going to provide me with a representation of the uncertainty, because if you put together all these models, you have a representation of the probability density in the space of Parton distributions. So in this case, each of these curves corresponds to a different neural network replica. So in green is the gluon, in orange is the up valence, and in blue is the up antiquark. So now the training starts, and you can see that the replicas, they start to come closer, which makes sense because they are trained to the same data. But also at some point, you keep having outliers. For example, you have this outlier here, and in the blue curve, you have these outliers here. Outliers imply that the 1 sigma error band still remains quite large. However, as the training goes on, every replica is going to be going better and better trained. So eventually, all outliers are properly trained, and the resulting error band just collapses into a much smaller error band. For example, you will see here now in orange. Now you don't see the error band because it's below the replicas, blue and green. So this is our outcome. What we provide, say, to the users is these Monte Carlo replicas, and each of them can be used to evaluate physical predictions. And when you take the envelope, for example, or the 68% confidence level, you can reliably assess the PDF errors in your physical prediction. Okay. Now, this was a little bit of motivation, since not everyone here. Yes.
I just have one question. So it seems like you, when using this deep neural networks, do you have any constraint on the number of parameters going to use in the end of the day? Like
no, not at all. In principle, one would like to have a model which is as flexible as possible, but the only limit is, in principle, is computational, right? If you have a network with 1,000 neurons, then that's probably an overkill. But conceptually, it can work equally well. So what we do is, for example, we do checks in which we demonstrate that our neural networks are redundant, meaning that if we take our default architecture and we remove, say, a bunch of the neurons, we still get the same result. Okay. So ultimately, it doesn't really matter which is your precise architecture, provided you are in the redundant regime. So it's flexible enough to describe your data.
Okay, thanks.
Now, so let me tell you now a bit what is the interplay between the PDFs and Higgs physics. Now, I'm sure you've seen in this conference this formula. This is the master formula for Higgs production at the LHC. So when you have to compute the cross-section for Higgs productions in the SM or in BSMS scenarios, you always have to combine two ingredients, as we said before. In red, you have the hard scattering matrix element, which you evaluate in perturbative QCD. And in blue is the partonic luminosity, which depends on the PDFs, and you have to extract from the data. Now, depending on the Higgs production channel, you will have different partonic luminosities. Higgs production in gluon fusion and TT Higgs production, they depend on the gluon-gluon luminosity. Vector boson fusion depends on quark-quark, while Higgs V or Higgs Z is quark-antiquark, because this is basically the Drell-Yan process. So clearly, providing robust predictions for Higgs production requires understanding the PDF all across the board, right? You cannot just focus on the gluon or the up quark. You simply need to constrain them as well as possible. And why? Well, because theory errors, including the PDFs, are likely to be a limiting factor for Higgs measurements at the LHC. So at the high lumen LHC, even if you have extremely precise measurements, the interpretation could be hindered by the fact that our theory is in some sense not as good as the experimental data. And this is one of the projections from ATLAS and CMS. And what you see, if you compute the total uncertainty budget in various production channels, is that theory errors are likely to become dominant in many cases. For example, in TT Higgs, theory error is about 4%, while the experimental error is much smaller, 1.5%. And here, the theory error includes scale errors, but also PDFs. So improving the PDF is essential if you want to make possible better Higgs measurements and the high lumen LHC. And this means also better BSM interpretations, because you can interpret these measurements in the framework of, say, modified couplings. And if your theory in the SM is insufficient, the bounds will be looser, but also in the SMEF. So now there are various groups that interpret data from the LHC in the context of the SM effective field theory, such as this one, which I was involved in. And this analysis, what they do is they fit the coefficients of higher dimensional operators to Higgs production and data from other processes. Again, this right now, we are not limited by theory errors, but at the high lumen LHC, we might. And this would imply that SMEF interpretations could be hindered because your PDFs are not good enough, for example. And it's interesting to note that the recent CDF2 MW measurement or anomaly emphasizes the crucial role that PDFs have for SM prediction and BSM interpretations. Because MW is interesting because it's not really a measurement, or it's an interpretation of your data, which relies heavily on the theory. What you do is you generate templates for, say, for example, MTW distribution, and then you feed them to your data. But if your templates or your SM theory is wrong, you're going to be biasing your result. So it could be that, for example, if you choose the wrong PDFs or PDF with the incorrect uncertainties, you're going to end up biasing the result. So I don't know exactly what is the explanation for the CDF measurement. It has been discussed extensively, but I think it's clear that if this is going to happen, say at the LHC, we would like to make sure the PDFs are as under control as possible, because this clearly is going to affect indirect BSM searches. So here I'm showing some comparisons of inclusive and differential LHC cross sections for Higgs production. For example, this is Higgs in gluon fusion, and you can compare NMPDF 4.0 with MSCC20 and CT18. And you see that three of groups are in regional agreement within uncertainties, with NMPDF being more precise than both MSHT and especially CT18. In other cases, the agreement is perhaps not as ideal. In some cases, for example, since our large Higgs gluon can be a bit different, you can have results also different at the LHC data. And this will require more measurements and actually more studies to understand what's going on. And this is something similar at the level of differential measurements, comparing between the results of various PDFs. Again, details doesn't matter. The point is that we now have an increasingly improved control on our PDF determinations. In some cases, we have a very good agreement, like Higgs production in gluon fusion, but in some others, perhaps a bit less. And it's good to keep understanding, what makes every PDF set similar or different from the others. Okay, where I am here. Now, as I mentioned before, in many LHC analyses, it's not convenient to use the individual PDF sets. Why? Because, for example, this requires that you have to deal with different Monte Carlo samples, and this can be not convenient. So a few years ago, we put together the so-called PDF-LHC combination of global PDF fits. And this is something that's especially useful for the experimental community, because this way they have to deal with a single PDF set for all the theory calculations, which accounts effectively for the information contained in the individual PDF sets. So these combinations do not bring in new information. They just represent a handy way of packaging the information contained by different individual PDF sets. So following a 2-year-long benchmarking study, this combination has been recently updated to PDF-LHC 21, which now is based on CT18, MSHC20, and NPDF 3.1. And the nice thing, especially for Higgs physics, is that it leads to fully consistent predictions. So, if you estimate your errors using the combination of 6 years ago and the ones with the current one, you get perfect agreement, but now with improved precision. So actually, this is an example that we are actually making progress, right? Because, we are, say, thanks to the better data and better theory, we lead to improved predictions for Higgs physics, which is what actually you need at the high luminance. And also we released several variants of PDF-LHC 21, such as Monte Carlo compressed replicas or Hessian reduced sets, which each of them are helpful to, for different experimental analysis. For example, this combination in general will not be a Gaussian distribution. Why? Because if you combine 3 different measurements, you don't expect to have a Gaussian in general. And you can have some kind of double hump structure. And you need methods such as the Monte Carlo compression to deal with them. And these are available. So here I'm showing the comparison of the gluon-gluon luminosity in the upper panels and the quark-antiquark luminosity in the lower panels. PDF-LHC 21 is the new combination in green, and PDF-LHC, which is the old combination in orange. So as you can see, there is excellent agreement within uncertainties at the level of central values. But if you look at the errors, you can see that the new combination benefits from smaller uncertainties. And for quark-antiquark, also the same, except if you go to very high masses. So any prediction for Higgs production in gluon fusion, TT-bar Higgs, or a Higgs acid production is going to benefit with this improved precision. And this is nice because it shows that we are actually making progress. So we are actually learning how to combine better our results to provide better predictions for Higgs physics. And the hope is that to keep moving in this direction to further narrow the PDF errors that affect Higgs production. So in this plot here, I'm showing more PDF sets, and now this is a comparison of Higgs production. In the x-axis is gluon fusion, y-axis TT-bar Higgs, this LHC14 TV, and these contours are the 2 sigma intervals. And here I show various PDF sets, CT18, MSH20, and PDF, the 2 variants, AVMP, the Atlas PDF fit, and then the 2 variants of PDF-LHC 15 and 21. So what you can see is that first, that the global fits are consistent, so they are all clustered in the same region. However, there are quite significant differences in terms of uncertainties. For example, NMPDF is much more precise than CT18 prediction. And you can see the outliers, AVMP16, with much lower predictions, and Atlas PDF 21, that leads to a higher prediction and also with much bigger uncertainties. So bottom line, global fits are consistent, but they exhibit a quite remarkable difference in the pattern of uncertainties. And this is the same if one looks at other LHC cross-sections, such as Higgs, sigma Higgs in the y-axis, and sigma Z is in the x-axis. So these are the kind of games that we have to understand a bit better. I mean, why different PDF sets can be disagreements sometimes? Well, this is something that we need to understand. Another point which is really important is that, so far for Higgs production, we've been using basically a QCD at next to next. However, if you would like to reduce the scale errors, you can go to one order higher. And this involves computing the partonic cross-sections at n to the cube leading order. And for Higgs, various groups have considered these calculations, and actually they have presented them. So this idea is that this is the first time is the Born term. Then you have NLO or the alpha S, NLO or the alpha S squares compared to the Born cross-section, and n to the cube leading order. These are insanely difficult calculations, but now we have them available for many interesting processes. And why we want this? Well, because it improves the precision and the accuracy of your calculation. So with the same measurement, you can enhance the physics reach. And also you can have a reliable estimate of how the missing higher orders are going to behave. And in the case of a Higgs, inclusive Higgs production, this is a rapidity distribution. You can see that at NLO is in green, then NLO is in blue, and then n to the cube leading order is in red. So these are a textbook example of how the convergence of the perturbative expansion should behave. However, one should be careful here, because n to the cube leading order is not full, because the PDFs are still next to leading order. So the question is this an issue? Well, we don't really know, because we don't have a PDF fits at next to the cube leading order. So there is a lot of activity in our community trying to exploit this recent progress to produce PDFs at n to the cube leading order, which is essential for Higgs physics, especially now that the HL-LHC is going to be at some point start operation. And for this, we need to do, we need several results. First of all, you need the Diglab splitting functions. Remember, we said that the PDFs evolve with a scale following this Diglab evolution kernel. The leading order was computed long time, almost 50 years ago. And then you have the second order 40 years ago. Next to next had to wait for more than 20 years. And right now we still don't have the full n to the cube leading order, but we have partial results. So we have results on low moments, we have results on large and small x limits, and so on. So we can construct some approximation, which is suitable for phenomenology. And this we also need to compute coefficient functions from DIS, heavy quark matching conditions. So this is not an easy task, but clearly, given that is key for LHC physics, is going to be very high in our priority list.
Well, I have a stupid question. Yes. What about in your processes when you calculate? What about soft Gluon resummations?
Yeah, that's a very good question. I think that soft Gluon resummation could be very useful in case that, for example, you don't have the exact result at n to the cube leading order for some process. Then you can use soft Gluon resummation to try to have an idea of how large or how small this correction is. So this could be used to construct some approximate k factor to the next order and use it into the PDF feed. So if the full result is not available, I agree with you that one could try to use resummation for these kind of things. It'd be quite useful. Okay, two more topics. First, about charm. So the common assumption in PDF feeds is that the proton contains only strange up and down quarks. And this makes sense because the charm quark is 1.3 GeV, while the proton is 1 GeV itself. So the charm is heavier than the proton itself. So in most PDF feeds, the charm PDF is generated purely perturbatively, so using Glab evolution. Essentially, you have a gluon which radiates a charm anti-charm pair. So in this respect, if there is no intrinsic charm in the proton, the charm PDF is trivial. It's simply a consequence of Diglab from light quarks and the gluon. However, it was predicted by Brodsky and collaborators more than 40 years ago that the proton could contain an intrinsic charm component. And this has been searched for extensively during 40 years, but so far there has been no unambiguous evidence that the proton actually contains charm quarks, and is of course a fundamental question for our understanding of proton structure. So we recently wrote a paper in which we demonstrate how one extract intrinsic charm. So in a nutshell, one starts from our, say, NMPDF global analysis. One constrains from the data the charm PDF in the 4th level scheme. And this charm PDF is the sum of two contributions. One, which is perturbative, so it comes from the big lab radiation, and another, which is from a potential intrinsic charm component. But they appear together. So what you extract from the data is always the sum of these two components. But now we can go backwards and transform the PDFs from the 4-flavor scheme to a 3-flavor scheme. Essentially, we remove the component which is perturbative. And at this point, we end up with something which is, if different from 0, can be identified in a very clear and theoretical way with the intrinsic charm of the proton. So this is our result for the charm PDF in the proton. So in blue is the result for intrinsic charm in the 3-flavor number scheme once you remove the perturbative component. This blue band is the PDF error, and the lighter blue band is the estimate of the scale uncertainties, which we assess by doing the matching from 4 to 3 flavor at n NLO at an n to the cube leading order. And this is a nice result because it shows that actually there is intrinsic charm in the proton. So we have this characteristic bump at x around 0.4, which is different from 0 at around the 3 sigma level. And actually it's not that different from the result, for example, the original Brodsky model. So we found this result, this is quite interesting because there have been a lot of discussions about whether or not there is charm in the proton. But now we start to have evidence that the global PDF analysis actually favors it. And a global PDF fit without intrinsic charm leads to a worse fit quality, especially for the LHC experiment. And actually, it gets better than that because there was also a measurement from the LHCb experiment late last year. They measured charm Z bosons together with charm jets. And this process is very interesting because if you look at the correlation, you expect that in the forward region, Z+charm is maximally sensitive to the charm PDF, where X is around 0.4. So this measurement here at LHCb is going to tell you whether or not there is charm in the proton or not. And
what about W plus C?
Sorry?
What about W plus C? That has been measured.
W plus C, it gives you information on the strange content of the proton, but not on the charm. Because then it's glue and strange. So you have this diagram here, and you put here a strange quark, then this is charm, and this is charm, this is a W.
Sorry.
So you use for strangeness, not for.
Yeah. Sorry.
So these are results from LHCb, especially in the most forward beam, which is the most interesting. What you see is that the prediction without intrinsic charm is a factor 3 below the data, and the prediction with intrinsic charm is basically spot on. And these two measurements are independent. So, our prediction and the LHCb data, they don't talk to each other yet. Once you put them together, they agree spectacularly. So the LHCb data provides an independent confirmation that after all, there is charm in the proton, and there is charm that carries about 0.5% of the total proton momentum. The fact that this is quite a small number, it tells you why charm is so difficult to find, just because it's a small signal. So you need a very careful methodology before you can tell apart what is charm, what is the contribution from strange, from up, down, and from other PDFs. So we find very interesting that there is a striking consistency between the direct constraints on the charm PDF, such as the ones from LHCb, but also from other measurements from F2 charm from EMC, and the direct constraints on the charm PDF. So if you put everything together, you get a significance of around 3.1, 3.2 sigma, which, in particle physics, we typically call this evidence from charm in the proton. So I think now it gives us a motivation that first is quite nice that after 40 years of these kind of games, we can still learn something generally new about the proton structure, but also that now this opens the possibility to study intrinsic charm in various ways, both at the LHC, but also at feeder facilities such as the Electron-Ion Collider, or also at the neutrino experiments. Okay, and since I have more or less 10 minutes until my time is over, let me tell you a little bit how do I see the future of PDF. So what's coming, what's the decade ahead for proton structure? So improving PDFs depends on progress on 3 main pillars. First, you need new data, you need to improve your methodology, and then you better theory calculations. New data will come from the high luminosity LHC, but also from the Electron-Ion Collider and from the forward physics facility. New techniques involve, for example, new machine learning methods, improving statistical frameworks, but also more robust feeds of LHC data, for example, you can do a joint feed of PDF with potential BSM effects, or you can combine different QCD objects. You can do a PDF feed, both of the proton PDFs and of the nuclear PDF. I will show 2 examples of this. But also we need better theory. So we need PDFs that tend to the cube leading order. We need PDFs which systematically account for theory errors, and we need PDF with QED and with electroweak corrections. So data, what can we expect from the PDF, say, in 20 years from now? So we did analysis in the context of the high luminosity LHC yellow report, which based on pseudo data from a variety of processes that could become available for the LHC. And then we compare them with the predictions based with some baseline. In this case was the PDF for LHC 15. And what we found is that actually the high luminosity LHC is going to have a very nice potential to further constrain the PDFs. So where reduction of the errors goes between a factor 20% to a factor 80%, depending on the, for example, if you assume a optimistic scenario for the systematic errors or a more pessimistic scenario. But in any case, it's something that is certainly there's a lot of room for improvement. Of course, it could be even better because these projections were based only on standard processes, say Drell-Yan, TOP, or JETS. But as the data becomes more abundant, one can think of different profs of the proton PDFs. So clearly, there is a lot of potential to further improve PDFs at the high luminosity LHC. Of course, this is something that projections are always a bit delicate. In real case, we have to see, for example, how the data looks like, how consistent our theory is with the data. And we have to account for many small effects like theory errors that might be negligible now, but at the high luminosity LHC, they will be important. Another question which is very important at the high luminosity is, how can you make sure that you don't reabsorb BSM into your PDFs, right? We are fitting more and more data from the LHC from higher energies. Maybe we are fitting away, the interesting signals that Isabel was mentioning in her talk. And this is a justified worry, right? Because in DSM, as I mentioned before, you write your cross sections as a function of the standard model PDFs and then some SM matrix elements. So when we do a PDF feed, we assume always the SM for the matrix element, and then we extract the PDFs from the data. However, if you have BSM physics, for example, let's say parameterized by the operators of the standard model effective field theory, then the prediction from the data should be something like this, where you extend the SM calculation with the dimension 6 SMEFT operators. And these are the Wilson coefficients, which are effectively your BSM parameters. So now, if you take the same data and you feed it with these new theory predictions, you're going to extract a different quantity. This quantity is called the SMEFT PDFs, because this is the PDFs that you can define in the context of the SM effective field theory, which is a different object. And the question is, one, how different are the SM PDFs with the SMEFT PDFs? And second, is it possible to quantify the risk of fitting away the PDFs, BSM into your PDFs? What tools we can develop to make sure that there is actually no risk of fitting away your new physics into your PDFs? And we've written a couple of papers with the group of Mario Biali and her collaborators. For example, in our latest paper, what we do is we take data from high mass Drell-Yan production, and then we extract the PDFs from a global fit that includes high mass Drell-Yan cross sections, where we compute the theory in the case of the effective field theory. And then we try to see to which extent the PDFs are different, and they are not. And what we find is that with current data, there is a limited interplay between the PDFs and the EFT fits. So this is not really a worry right now. But at the high luminosity LHC, actually, EFT effects, if present, would be reabsorbed into the PDFs. In the case of high mass Drell-Yan, if you have some EFT operator that, for example, increases the EFT, the Drell-Yan cross-section, this could be reabsorbed into the PDFs. So in this paper, we also developed some techniques that one can use to tell apart, what is the, to which extent, one can separate QCD effects from BSM effects. For example, the scaling with the energy is different from BSM and QCD, and one can use it to tell it apart. So this is something that we are now starting, but clearly at the high luminosity is a point of attention. We want to make sure to extract the best possible PDFs, but also without fitting away the potential BSM effects, which would be pretty bad. There will also be the constraints from the Electron-Ion Collider, in which several groups from India are also directly involved. And the EAC will provide a unique chance to study QCD matter, polarized PDFs, nuclear PDFs, 3D structure, this is something which is quite exciting, but it also will require to improve our methodology. Because, for example, right now, we extract proton PDFs, nuclear PDFs, and polarized PDFs separately. But at the EAC, this is not justified anymore. Observables depend on all these 3 or even 4 QCD objects. You will need to extract at the same time proton PDFs, nuclear PDFs, and fragmentation functions of polarized PDFs. And this requires really stepping up our game in terms of QCD methodology. And for this, we are making progress already. So we are making progress towards extending the NMPDF machine learning framework towards fitting only our proton PDFs or nuclear PDFs to combining them into a single analysis. So our goal is to have a joint extraction of the proton structure from A = 1 to A = 1008. And eventually you can extend these two PDFs to polarized PDFs and to fragmentation functions. So here are some preliminary results. Clearly, we still have some work to do, but this is important for the future of our community. And since I'm running out of time, just 2 more slides. Another possible constraints on the PDF will be given by the Forward Physics Facility. This is a proposal to install a new underground cavern at CERN. And the idea is that at the LHC, when you collide protons, you generate a lot of forward particles, such as the mesons, which then decays into neutrinos. So if now you go apart, you go far from the interaction point, and you screen everything else, you will have a very clean flux of essentially high energy neutrinos that you can use to test QCD at small x or to do neutrino DIS at the TeV scale. So if you look at the kinematical range, for example, these kind of machines, the FPF, will provide access to very small x and to very large x at lower scales. So it's a really unique machine to study ultra small x proton structure, which is important for application in astroparticle physics, but also to do neutrino DIS at the TeV scale. So it's a new window to proton and nuclear structure with neutrino probes, which are very powerful because they essentially constrain light, quark and antiquarks in a way which is complementary to that of the EAC or other experiments. Okay, so I don't have time for more, so let me just go to the summary. So I've tried to motivate that the precise understanding of the quark and gluon structure of the proton is central for the physics program of the LHC and all the future upgrades, of course. That progress in PDF determinations have led to precise predictions for Higgs production, which in turn are essential to a robust characterization of the Higgs sector and for searching for BSM physics, for example, in terms of modified couplings or effective field theory operators. But that we still have a lot of work to do, and that PDF fits in the coming decade will benefit first from new experimental measurements, high-lumen LHC, EAC, or the FPF, from better theory calculations, QCD and electroweak, but also for methodological improvements such as sophisticated artificial intelligence techniques. So that's everything from my side, and thanks for your attention.
Yeah, thanks a lot, Professor Juan, for the wonderful talk. And I could not follow most of it, but at least I got an overview of certain things which were missing earlier in my understanding. So if any of you have any questions, you can raise your hand. Sunny, you have a question? Yeah, Arnav?
Can you go to this the slide where you were talking about machine learning for the NMPDF? They're really very promising results.
What was the slide? Sorry.
It's where you had the neural network.
Yes. This one.
Yes.
Or this one.
I have, yeah, I also had the question related to the other plot that you were, the video that you were showing. But yeah, so first of all, it's just from my understanding, it's not a question. So what exactly, I mean, so if I understood correctly, it's like you use the data to train this network to get I mean, you basically regress the PDF as a function of X and ln X.
Exactly. So we have to construct a model for the X dependence on the PTFs. And our model in this case is basically an artificial neural network. And then we train the parameters of this network to describe the data in the best possible manner.
Exactly. Okay. Okay, so thanks for this, the clarification. And the question that I had is, when you were showing the video, at some point we saw that it's almost like there are not many fluctuations or outliers. But how do you decide where to stop? I mean, like that's.
Yeah. So these are a good question, and the method we use is called look back cross validation stopping. The idea is that for each of these curves, we take the data and we do split it into two subsets. One is used for the training, and the other for the validation. And then we monitor the chi-square to both data sets. So what happens is that you can see when you are going too far or too early, if both the data from the chi-square and from the training, so if the chi-square from both the training and the validation samples is decreasing, this means that you are still learning something. At some point, you will see that the chi-square of the validation will start to increase. And this means that you're actually fitting noise at this point, and then you should stop. So these outliers correspond to basically getting stuck in local minima, but you see that they're still learning because the two chi-squares are still going down. But once they are properly learned, you will see that the validation will start to increase. And this is a sign that you should stop the training there because you would be overlearning.
Okay. I mean, it's basically the chi-square, and then you follow the standard procedure, like overfitting or underfitting, something like that.
Yeah, exactly.
Yeah,
it's a pretty standard machine learning criterion for stopping of the networks.
Okay, thank you.
Yeah, from TFR D406.
Yeah, Juan Kajari here. So it is nice to see that we are able to put hand on the charm content of the proton. So what will be the plan for the bottom content of the proton? Is that,
that's a very good question. I think that this is something. So in our to-do list, we have, say, 2 follow-up projects. First, we would like to understand what happens if we parameterize the bottom PDF. Do we still get a non-zero component, or it's just zero within uncertainties? One difference is that while for charm, we have lots of data that provide some information, for bottom, this is less so. So actually for bottom, there is not much we can do, at least with current data. So we will try it, but my guess is that we'll get just a big error band. What is perhaps more interesting is that to try to constrain the intrinsic charm asymmetry, because in some models, charm and anti-charm, they are different. Yeah. And we will try to see whether or not with current data, we can tell them apart. Because, for example, the Brodsky model predicts asymmetric intrinsic charm, while other models favor an asymmetric. So this, we should have the data to investigate. This is something that we plan to do in the next month.
So by HL-LHC, you are expecting to have considerable improvement in the Parton distribution, yeah, by of the order of 10%, or ballpark figure if we say, because we know quite well the valence quarks, and the gluon also is getting constrained. So it is mostly this C or these are the. Yeah.
Exactly. I think the important point is that these are a very small signal. So in absolute terms, intrinsic charm is just a few per mil effect, right? So it's not going to modify a lot your valence quarks or your gluons. However, it can be identified. So it's a small thing, but it's different from zero. And this is something why it's so difficult to identify it, because it will not change a lot your quarks and the gluons, yet still you have to be sensitive enough to be able to identify this small fluctuation.
So while your talk was going on, I was wondering, because this, if I remember correctly, about 20% of the W production is coming from this heavy quark, the initial state. So if we measure the W production very well, which we do not have problem at LHC, so we still cannot have much undo, because it's all mixed up, S contribution, charm contribution, etc.
Everything is mixed, but you're perfectly right. Actually, the dominant constraints on the blue curve is the inclusive data on W and Z production at the LHC. So what really drives intrinsic charm in our analysis is the very precise measurements of W and Z at the LHC. Or you say because there is a strong, say, strange charm component, for example, in W production.
Okay, one last question is that what about these transverse TMDs, transverse momentum distributions? Is it a completely different ballgame, or?
I think it's a different game in the sense that at the LHC, it's unclear that they are relevant.
Yeah.
They are interesting to study, the proton from some other perspective, and many groups are actively working on that. But I think the TMDs are something more from the EAC physics program as opposed to the from the LHC. I don't think you can learn more about TMDs from the LHC, while the EAC will study them in excellent detail.
Okay. Thank you.
Okay, thanks.
Very nice talk. Thank you so much. You explained all the crucial things about LHC physics. Very nice. Thank you.
My pleasure.
Yeah, thanks a lot once again. I guess there are no more questions. And thanks for, what should I say, we were running late, and thanks for being patient too.